The Massachusetts Institute of Technology, or MIT, is where the brightest minds push the boundaries of science, constantly seeking to unravel the mysteries of the universe. For decades, MIT has been a hub for innovation, where curiosity and ambition drive researchers to explore the unknown. Recently, their focus has turned to quantum mechanics, the bizarre world of atoms and particles, where reality defies common sense and the rules of classical physics no longer apply. In this strange realm, the impossible becomes possible. Here, particles can exist in multiple places at once, a phenomenon known as superposition, which challenges our everyday understanding of how things should behave, and be linked across vast distances through entanglement, a mysterious connection that Einstein famously called spooky action at a distance. This isn't just theoretical, these discoveries are laying the foundation for future technologies like quantum computers, which could solve problems impossible for today's machines, and unhackable networks that promise unprecedented security. At the heart of this research is quantum teleportation, not moving objects through space, but transferring the exact state of one particle to another, instantly, no matter the distance between them. Imagine sending a perfect blueprint to a friend, allowing them to build an identical structure without ever touching the original. Information, not matter, is what's being transmitted. MIT's Dr. Eris Thorne and her team set out to teleport not just a single particle, but a small, complex system, an ambitious leap forward in the field. Their goal? To lay the groundwork for teleporting more complex information, opening the door to new possibilities in science and technology, maybe even molecules one day, which could revolutionize everything from medicine to materials, science. The experiment was meticulously planned, every variable controlled, every calculation checked and rechecked, as the team prepared for the unknown. But the quantum world had a surprise in store, one that would challenge everything they thought they knew and push the boundaries of science even further. To understand MIT's breakthrough, let's first clarify what quantum teleportation really means. It's a concept that often gets confused with science fiction, but the reality is even more fascinating. Quantum teleportation isn't about moving physical matter from one place to another, like in Star Trek. Instead, it's about transmitting a particle's quantum state, its unique identity and information, using a phenomenon called entanglement, which links particles in a mysterious way. Entangled particles are like a pair of gloves. If you find a left glove, you instantly know the other is right, no matter how far apart they are. This connection is instantaneous and defies our everyday intuition. In the lab, scientists use three particles: Alice, which holds the state to be teleported, and Bob and Charlie, which form an entangled pair. This setup is crucial for the process to work. Alice and Bob are measured together, which scrambles Alice's state and breaks the entanglement between Bob and Charlie. This step is delicate and must be performed with extreme precision. The result of this measurement is then sent to Charlie's location using classical communication, like a phone call or an email, but with quantum data. With this information in hand, scientists perform a specific operation on Charlie, transforming it based on the data received. Suddenly, Charlie becomes an exact replica of Alice's original quantum state, as if the information has leapt across space. The original Alice is gone, her information transferred, not cloned. This ensures the no cloning rule of quantum mechanics is respected. This process forms the backbone of quantum communication and quantum computing, opening doors to ultra-secure networks and powerful new technologies. It's a process that's incredibly precise, delicate, and, until now, was thought to leave nothing behind. No trace of the original state. But MIT's experiment would reveal a hidden layer to this process, suggesting there's more to discover beneath the surface. The quantum world, it seems, always has another trick up its sleeve, keeping even the brightest minds guessing. Dr. Thorne's team wanted to teleport not just a single particle, but a cluster of 5 photons, a quantum word instead of a letter. These photons were arranged in a complex, delicate configuration, holding intricate quantum information. The experiment took place in a vibration-proof, shielded MIT basement lab. First, they created the 5-photon cluster, the message. Then, they generated entangled photon pairs, sending one from each pair to the receiving station. At the sending station, the 5-photon message interacted with local entangled photons. A series of delicate measurements imprinted the message onto the entangled pairs, destroying the original. The measurement results were sent as classical data to the receiving station. There, scientists used precise laser pulses to reconstruct the original quantum state. If successful, the 5-photon word would reappear at the destination, perfectly teleported. It was a leap toward building the quantum networks of the future. The team expected a straightforward result. The original 5-photon cluster would vanish, and a perfect copy would appear at the receiving station. Quantum mechanics' no-cloning theorem dictated that only one version could exist. The original destroyed, the copy reborn. The process was designed for a one-to-one transfer, like moving a priceless sculpture from one museum to another. Quantum experiments are fragile. Even tiny disturbances can ruin the process. The team aimed for high fidelity, a measure of how closely the received state matched the original. Success would mean a clean transfer, a high-fidelity copy, and confirmation of quantum theory. They expected to publish a solid, incremental advance. But the universe had other plans. What they found would rewrite the rules. The experiment was a resounding success. The 5-photon cluster was not only teleported, but the fidelity of the transfer exceeded even the most optimistic predictions. The team celebrated, believing they had achieved a new milestone in quantum communication. But as the data poured in, a junior researcher noticed something odd. A faint, structured signal at the sending station, where, according to theory, there should have been nothing at all. It was as if a shadow of the original cluster lingered behind. This was the first sign of what would soon be called the quantum after-image, a phenomenon no one had anticipated. It wasn't made of photons or any physical particles, but rather a ghostly, persistent pattern of information that seemed to linger in the quantum vacuum itself. The original cluster was gone, teleported away, yet a memory of its structure remained, a whisper in empty space, a trace that defied conventional explanation. The team re-ran the experiment, meticulously checking every variable. Each time, the after-image appeared, lasting only microseconds before fading, but always unmistakably present. It seemed to violate the no-cloning theorem. Not a perfect copy, but a real, information-rich echo, as if the act of teleportation left a scar in the fabric of reality. Attempts to measure it directly made it vanish instantly. Only its subtle influence on other particles and systems revealed its fleeting presence, like a ripple in a pond after a stone is thrown. The after-image was a fragile scar on reality, left by tearing information from one place and reconstructing it in another, hinting at deeper connections within the quantum world. Dr. Thorne's team realized they'd uncovered a new phenomenon, one that opened a Pandora's box of questions about the nature of information, memory, and the very structure of reality itself. The quantum world had revealed a hidden layer, challenging the very foundations of physics and forcing scientists to rethink what was truly possible. The after-image was undeniable, and it demanded explanation. The scientific community was abuzz, eager to understand this mysterious echo. For Dr. Thorne and her team, the scientific adventure had just begun, and the quest to unravel the secrets of the quantum after-image was only getting started. Dr. Thorne's team spent months ruling out every possible error, rebuilding equipment, enhancing shielding, repeating the experiment. The after-image persisted. Only after exhausting all explanations did they publish their findings and share them with trusted colleagues. The initial reaction was disbelief. The no-cloning theorem is a bedrock of quantum mechanics. Many assumed it was a mistake, until labs in Germany and Japan replicated the result. The after-image was real, reproducible, and impossible to ignore. Theoretical physicists scrambled to explain it. Was the no-cloning theorem incomplete? Did information have a hidden texture? The discovery forced a re-evaluation of quantum information. Suddenly, the after-image became the hottest topic in physics. Could this residual information be accessed or used? The MIT experiment was a humbling reminder. Even our most solid theories are just sketches of a deeper reality. When news of the quantum after-image hit the mainstream, public fascination exploded. Headlines screamed of ghosts in the atom and teleportation's spooky side effect. The idea of a lingering echo captured imaginations and fears. People wondered, if teleporting particles leaves a ghost, what about teleporting people? The discovery sparked debates about identity, consciousness, and the risks of new technology. Scientists found themselves explaining the subtle reality behind the dramatic headlines. The after image became a symbol of science's power and its potential dangers. It was a reminder that every discovery changes how we see ourselves and our universe. The quantum after image is more than a strange discovery, it's a lesson in the unpredictability of science. The MIT team's greatest achievement was their willingness to investigate the unexpected, not just confirm what they knew. True breakthroughs often come from surprises, not plans. The afterimage was MIT's accidental spice, adding new flavor to our understanding of reality. It reminds us, progress means adapting when things go awry, and every new technology brings unforeseen consequences. The discovery is a humbling gift, showing our theories are just sketches of a grander reality. It didn't answer all questions, it created new ones. What is information? What is reality? The echo in that MIT lab is a whisper from the universe, urging us to keep exploring. In science, the greatest discoveries are often the ones we never expected.